In section 4.3, we're going to look at properties of logarithms. I've created a logarithmic properties handout to summarize all the key rules and information in this section. The logarithmic properties you learn in this section can be very useful when we solve exponential and logarithmic equations in section 4.4, and they also can be very useful in calculus when finding derivatives of complex functions. In the first part of the chapter, we're going to look at three individual rules: the product rule, the quotient rule, and the power rule. And these rules all have their basis in rules of working with exponents. We'll look at the product rule, which states that the logarithmic expression of some quantity m times n can be expressed as a sum log to the base b of m plus log to the base b of n. The quotient rule says that the expression log to the base b of m divided by n can be expressed as log to the base b of m minus log to the base b of n. And then the power rule says that some logarithmic expression log to the base b of m to some power p can be re-expressed where that power p comes out front as a multiplier by the expression log base b of n. So let's look at these rules individually. The first rule we will examine is the product rule. And if you remember your rules of exponents, if you have some base b to the m power and the same base b to the n power, well, when you multiply these two values, you would add the exponents. Now remember, for a specified base b, the logarithm of that numerical value really gives you the exponent that you would see here, m and n. So it makes sense that the logarithmic log of base b of m times n would just be the sum of log base b of m plus log base b of n, just as you were adding m plus n here. Remember when working with this rule that the quantities b, capital M, and capital N all have to be positive real numbers, and b cannot equal 1. So remember, we can't have any negative values for our logarithmic expressions here. Now let's look at example 1. On example 1, on page 493 of your textbook, we have this expression, log to the base 4 of 7 times 5. So 7 is really our value capital M in our rule here, and 5 is capital N here. So we'll just now decompose this expression into the sum of the individual logarithms. So it'll be log to the base 4 of 7 plus log to the base 4 of 5. In part B, we have log of 100x. So 100 would be capital M, and x would be capital N. So again, we'll decompose that expression into log of 100 plus log of x. Now remember, when you see log, that's really the common log, which is our base 10 logarithm function. And depending on the numbers you might have in an expression, sometimes you can evaluate those logarithms. Remember, here our base is really 10, our value is 100. 10 to the second power, 10 squared is 100. So in this particular example, log of 100, you can actually evaluate to 2, and then we'll have plus log x. So this will actually be the true simplified final answer, 2 plus log of x. The next rule is the quotient rule. And if you remember your rules of exponents, if we have some quantity b to the m power divided by b to the n, the bases are the same, we would subtract the exponents. We would have b to the m minus n. So again, logarithms really represent these values m and n. So if we have an expression log to the base b of m divided by n, we can decompose that expression to log to the base b of capital M minus log to the base b of capital N. And just like we saw with the product rule, b, capital M, capital N have to be positive real numbers, and b cannot equal 1. Let's look at example 2. Example 2 on page 494 of your textbook has two parts. Our first expression is log to the base 7 of 19 divided by x. So 19 will be capital M in our definition, and x will be capital N in our definition. So we'll decompose this expression as log to the base 7 of 19 minus log to the base 7 of x. In part B, we have an expression involving the natural log function. So natural log of e to the third power divided by 7. So e to the third power is our capital M in our definition. The 7 is capital N. So we'll decompose this expression. This will be natural log of e to the third power minus natural log of 7. Now remember, the natural log function is really the log function to base e. And because we have an expression with base e here, remember, e to what power would give me e to the third power? Well, that exponent or power would be 3. So much like we saw in example 1, this expression can actually be evaluated and simplified. And so the true final answer will be 3 minus natural log of 7. The last rule we will look at is the power rule. Remember, with your exponent rules, if we have some quantity b to the m and it's raised to the n power, we would multiply those exponents m times n. So again, if we have a logarithmic expression that represents this exponent and it were raised to a power, we'll multiply by that power. And that's what we see here. So if we have this expression log to the base b of some value capital M raised to the p power, we can take that exponent p and move it out in front of the logarithmic expression and then multiply p times log to the base b of capital M. And again, b and m have to be positive real numbers, b cannot equal 1, and p, the exponent, also has to be a real number. Now, let's look at example 3. Example 3 on page 495 first gives us in part A log to the base 5 of 7 to the 4th power. So we'll just apply the power rule. The 7 is capital M, 4 would be p in our definition. So this will just be 4 log to the base 5 of 7. So we can take that power that we see, in this case 4, and move it out front as a multiplier in front of the logarithmic expression. In part B, we have natural log of square root of x. Now, when you have any radical term, you want to express that with rational exponents first. So I'm going to write square root of x as x to the 1/2, and now we can apply our power rule. The power is really 1/2, x is capital M in our definition, but we'll move this power of 1/2 out in front, and so the final answer will be 1/2 natural log of x. In part C, we're given the expression log of 4x to the 5th power. And we'll actually see a preview of our work with expanding logarithmic expressions in this problem, where we're actually going to use a couple of our rules. Notice we have this exponent of 5, so the first rule we'll apply is the power rule. So this would be 5 log of 4x. But if you look at this part of the expression, this is really a multiplication or a product, 4 times x. So now we will apply the product rule. Now just be careful, the 5 is a multiplier out in front of this expression, so we'll have log of 4 plus log of x. Just make sure you distribute that power of 5 as a multiplier in front of each part of the expression. Now that we've looked at the power rule, we can also revisit the simplification in part B, where we had natural log of e to the 3rd. Using the power rule, we could move this 3 out front, and then remember, based on the properties of 1, the natural log of e would evaluate to 1. And then 3 times 1 is, of course, 3. So now you can look at this simplification, and you can apply the power rule in a situation like this, if you would like. Now, do pencil problems 1, 2, 3A, and 3B.